Hello there and welcome to Chemistry Made Simple. Now this is a GCSE or Key Stage 3 level video about covalent bonding molecules and simple molecular structures. However, if you're starting off the A-level course, you would find this really useful revision. So in this video I'm going to cover firstly what a covalent bond actually is. Then I'm going to draw out for you and show you how to draw out molecules of hydrogen, oxygen, nitrogen, chlorine, hydrogen chloride, water, ammonia, carbon dioxide, methane, ethane, chloroethane and ethene. And then we'll have a look at properties of simple molecular structures. So firstly, let's have a think about what a covalent bond actually is. Now, when we had ionic bonding, we had to have a metal reacting with a non-metal. In covalent bonds, we've got pairs of outer shell electrons which are shared between atoms of non-metals. Now, this forms a really strong bond, and the bond is actually the electrostatic force of attraction between the nuclei and the shared pairs of electrons. Well, what do I mean by that? Well, let's have a look. Let's make this a bit bigger. So to have a covalent bond, we have a shared pair of electrons between two atoms like that. Now, we normally show one of the element's electrons as dots and the other as crosses. So if I fill up the outer shell, now really importantly, it's only ever pairs of electrons from the outer shell that are shared. Okay, we never have any shared electrons from any of the inner shells in an atom. Now, electrons, as we know, are negative, and any nucleus has got a positive charge because nuclei contain protons which have got a positive charge. Neutrons, also present in nuclei, don't have a charge at all. So therefore we get electrostatic attraction between a nucleus and the shared pair coming from both atoms. So if we go back to the definition, so we've got a strong electrostatic force of attraction between nuclei, that's got to be plural, and the shared pair or shared pairs of electrons. A covalent bond is actually the strongest type of bonding. Now, covalent bonding always involves outer shell electrons, or sharing of pairs of outer shell electrons. And it's really important that we know how to use our periodic table to work out the number of electrons in the outer shell of any element. Well, you have a look at the group number that the element is in. So everything in group 1 will have 1 electron in its outer shell. Everything in group 2, 2. Don't worry about the transition metals, that great big block in the middle. Then we've got group 3, 4, 5, 6, 7. And the group at the end doesn't form bonds, so let's not worry about that. Now, if we have a look at the element hydrogen, so the molecular formula of hydrogen is H2, which means it's diatomic, and every atom of hydrogen has got 1 electron in its outer shell. So all we do is we put the only electrons as a shared pair between the two atoms. Now, if you look at it, we've got 1 electron from each of the atoms, a cross from one of them, a dot from the other. Now, hydrogen only needs 2 electrons to have a full outer shell because hydrogen's only got 1 shell. It's the only atom that will form a covalent bond where there's only 2 electrons. So this is our covalent bond here, and we call it a single covalent bond, and we can show this using the displayed formula as H with a single line attached to another H. A single line represents a single covalent bond, or 1 shared pair of electrons. Now, if we have a look at oxygen, it's diatomic as well, and it's got the formula O2. Now, if you find oxygen on the periodic table, it's in group 6. Therefore, every atom of oxygen has got 6 electrons in its outer shell. So, let's put 1 shared pair of electrons in the middle, and let's put the other 5 electrons in place. So we'll do that for both of the atoms. Now, oxygen, with having more than 1 shell, needs 8 electrons to have a full outer shell. So let's count them up. So we've got 2 there, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right, this doesn't work then. So it can't be a single covalent bond. We can't have just one shared pair of electrons. So let's rub this out. Let's start again. So let's put two shared electrons in the shared bit. So one shared pair and another shared pair. And therefore we've got 4 electrons left to put on each atom. Now, we'll have a little check now. And we've got 1, 2, 3, 4, 5, 6, 7, 8. So that works. And if we look at the other oxygen, 1, 2, 3, 4, 5, 6, 7, 8. So that works as well. So if I put the symbols there for oxygen. Now this is what we call a double covalent bond, which is 2 shared pairs of electrons. And we could show the displayed formula as O with 2 lines connected to another oxygen. 2 parallel lines like that shows you a double covalent bond. Let's have a look at nitrogen. So nitrogen, another diatomic element, N2. Now this actually needs 3 shared pairs of electrons in the middle. So what I'm going to do is I'm going to make this a little bit bigger like so. And I'm going to put 3 shared pairs like that. 2, 3, 4, 5, 6. Now nitrogen's got 5 electrons in its outer shell because it's in group 5. So therefore we've got 2 electrons left to put on this atom and only 2 electrons left to put on this atom. Now let's have a little count up. So if we look at our shared pairs, we've got 1, 2, 3, 4, 5, 6 over here, 7, 8. So that's okay. And then once again on this atom, 1, 2, 3, 4, 5, 6, 7, 8. So all is well there. And really importantly, there are 5 dots and 5 crosses showing that 5 electrons have come from one of the nitrogens and the other 5 electrons have come from the other nitrogen. Now we can show this as N with 3 lines connected to N to show that we've got a triple covalent bond or 3 shared pairs of electrons. Now you don't ever get any more than a triple covalent bond. Okay, let's move on to and have a look at chlorine. Now chlorine, another diatomic element, has got the formula Cl2. Now because chlorine's in group 7, it's got 7 electrons in its outer shell. So all we do is we put a shared pair between the 2 atoms and we've got 6 electrons to put that are not involved in bonding. So chlorine only has a single covalent bond, and that would apply to anything else in group 7, and we could show it as Cl, a single line for a single bond, 1 shared pair of electrons attached to another Cl. Now everything that we've done so far has been an element. This is our first compound, HCl, otherwise known as hydrogen chloride. Now hydrogen's got 1 electron in its outer shell, chlorine's got 7. So in this case we're going to get a single covalent bond between the H and the Cl. So we'll put our shared pair of electrons there and we'll put our other 6 electrons from the chlorine here. So we could show that as H single line Cl because we've got a single covalent bond or 1 shared pair of electrons. And just having a little check, so we've not done that for a while. We've got 1, 2, 3, 4, 5, 6, 7, 8. So chlorine's okay. And hydrogen's okay just with 2 because hydrogen's only got 1 shell. So if we look at another compound, this is H2O. So this could be a molecule of water, ice or steam. Now, the smaller atoms are the hydrogens. So if we label those first, and the larger atom is the oxygen. Now, let's put a shared pair in the overlap between each of these atoms. And then, if we have a think about oxygen, we've put 2 of its electrons in, so we've got another 4 electrons to put. Now, importantly, what we've got here are 2 single covalent bonds, and these are called 2 non-bonding or lone pairs of electrons. Now, we could show a displayed formula for water, and we could show it like this. So O, you might show it like that. When we get to A level, we tend to show the correct bond angles like this, and we can show the non-bonding pairs of electrons like that. So that's water with two single covalent bonds. So let's have a look at ammonia with the formula NH3. So we've got 1 nitrogen and 3 hydrogens. And let's have a look at the electrons in a molecule of ammonia. Now, what that needs us to do, well, tell you what, let's label the atoms first. So label our hydrogens here and our N for nitrogen. And we'll put a shared pair in each overlap, like so. Now, we've put 3 electrons from nitrogen in. Nitrogen's got 5 in its outer shell, so let's put the remaining 2 there. And let's have a little check and make sure everything's right. So nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. So that's okay. And then each hydrogen's only got 1 shell, so it only needs 2. So we've got 2 there, 2 there, and 2 there. So all is well. So that's a molecule of ammonia. And if we want to do the displayed structure for ammonia, or the displayed formula should I say, we can show it like this. And we could even show the lone or non-bonding pair of electrons there like that. Now if we have a look at carbon dioxide, that's got the formula CO2. So in every molecule of carbon dioxide there's 1 carbon and 2 oxygens. Now, I'm going to put the atoms in the correct order, in case you want to put this on pause and have a go at this yourself. Now, I'm showing crosses for the electrons in carbon, dots for the electrons in oxygen. So if you want to have a go, put this on pause, but I'll do the answer in a few seconds. Now, carbon dioxide actually has 2 double covalent bonds. So we'll show 2 shared pairs of electrons in each overlap. So that's the 4 electrons from the carbon atom now gone, now used up. So what we can then do is show the other 4 electrons in each outer shell for oxygen, like so. And therefore we can do the displayed formula of carbon dioxide like this. That's C double bond O, like that. Now, just have a little check and make sure everything's correct. If we have a look at any atom, well, oxygen's got 1, 2, 3, 4, 5, 6, 7, 8 electrons. Fine. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. That's fine as well. And this oxygen here, 1, 2, 3, 4, 5, 6, 7, 8. And we've got 6 electrons from each oxygen and 4 electrons from the carbon. So that's a molecule there of carbon dioxide. So if we have a go at another compound called methane. Now methane's got the formula CH4. So every molecule of methane has got 1 carbon and 4 hydrogens. Now, by all means, put this on pause, have a go at it yourself, and I'll go through the answers in a couple of seconds. Now, methane's got 4 single covalent bonds, so if we put a dot and a cross between each atom like this, and we've got 4 crosses that come from the carbon, because 1 carbon's got 4 electrons, and we've got 4 dots, so 4 electrons that come from each of 4 hydrogens. The only reason why we use dots and crosses is so we can tell later on where the electrons have come from. And 1 molecule of methane we can show like this. So we've got 4 single covalent bonds like that. Now if we have a look at ethane, so C2H6, so each molecule of ethane has got 2 carbons and 6 hydrogens. Now if you want to have a go at yourself, put this on pause, I'll be glad of the break, and I'll go through the answer in a few seconds. Now importantly, we show the X's as the electrons for carbon, so the single bond between the 2 carbons then will show as a pair of X's. Every other covalent bond is going to be a dot and a cross, like so. So if we just check that everything's right, we should have 6 dots, so 1 dot from each hydrogen. So I've got 1, 2, 3, 4, 5, 6. That's absolutely fine. We should have 8 crosses because we've got 2 atoms of carbon. So 1, 2, 3, 4, 5, 6, 7, 8. All's well there. The 2 carbons have got 1, 2, 3, 4, 5, 6, 7, 8 in their outer shell. Same with that one there. All is well there. And each hydrogen, if you look round, has got 2 electrons because remember, hydrogen has only got 1 shell and therefore only needs 2 electrons to fill it. Now, we could show this once again as a displayed formula. So all the bonds are single. So we could show a molecule of ethane like this. Now, you might be asked to do something like C2H5Cl. So let's have a look at how that might be different. So if you look at that carefully, all I've done is I've replaced a hydrogen with a chlorine. Now, a lot of people forget to put the extra 6 electrons in the outer shell of the chlorine. So finally, we're going to have a look at ethene. So we've got the formula C2H4, so 2 carbons and 4 hydrogens. Now I've put the atoms in the correct place in the molecule for you, so if you want to put this on pause and have a go at it yourself, you can do. I'll go through it in a couple of seconds. Now you may well have worked out that we need a double covalent bond between the 2 carbons. So I'm going to put the 2 pairs of electrons there. I'm showing those electrons as dots because both of those pairs come from carbon atoms. Then I'm going to show a dot and a cross in each of the other single covalent bonds. Now, if we just have a look at this carefully. So for the carbons, we've got 1, 2, 3, 4, 5, 6, 7, 8 electrons, so all's well there. 1, 2, 3, 4, 5, 6, 7, 8, so we're okay there. And each hydrogen has got 2 electrons, and it only needs 2 because it's only got 1 shell. Now, we can show the displayed formula of ethene like this. So a double covalent bond between the 2 carbons and a single covalent bond, or 1 shared pair of electrons between each carbon and hydrogen. Now, everything that I've drawn in this video has been a molecule. Now, what is a molecule? Well, it's a fixed number of atoms joined by covalent bonds. Now, the type of structure that we get is called a simple molecular structure. Now, I've mentioned before that covalent bonds are very, very strong. How come then all of these molecules, apart from water, will be gases at room temperature? Well, the answer is that when you boil something like this, you are not breaking covalent bonds. You are overcoming intermolecular forces of attraction. Now, between each molecule, we've got intermolecular forces of attraction which are weak. So I can show those like this. So therefore, the properties of simple molecular structures are low melting point and low boiling point, because we're overcoming intermolecular forces of attraction rather than breaking covalent bonds. And they never conduct electricity because there are no charged particles that are free to move. Okay, well, thanks for watching. That's covalent bonding, molecules and simple molecular structures, hopefully made simple.